Hi students, good morning. Welcome to this video session. I remain Samuel Dominic Chukwu Emeka, aka Sam Dom for Peace. In this video session, we shall continue our study on modular arithmetic and algorithms. In this video session, we shall solve and check a system of linear congruences using the Chinese remainder theorem. In another video, we shall use the back substitution method. So we actually have two methods of solving a system of linear congruencies. We will use the Chinese remainder theorem and the back substitution method. The transcript of this video can be found on this website, www.modular-arithmetic.appspot.com, www.modular-arithmetic.appspot.com. So the transcript of the video, the link to the video, and the calculators, you can use the calculators on this website to check your work as well. We are going to check it, but you can also use the calculators to check your work as well. So let's say you what if somebody asks you this question, when you have a number divided by 5, okay, and the remainder is 4, and you have the same number divided by 7 and the remainder is 6. What is that number? Okay, so this is the question here. When a number is divided by 5, the remainder is 4. And when the same number is divided by 7, the remainder is 6. What is the number? So this kind of question, if somebody asks you this kind of question, you know that it deals with congruency, linear congruencies. We are going to deal with this only when the moduli are relatively prime. So, but let's get back to the question, okay? A number, when a number is divided, when a positive integer is divided by 5, the remainder is 4. So this means, okay, let the positive integer be x. Let the positive integer be x. So remember, we said when the number is divided by 5, the remainder is 4. So this means that x is congruent to 4 in mod 5. So when the number is divided by 5, the remainder is 4. When the same number is divided by 7, the remainder is 6. So we have x is congruent to 6 mod 7. What is the number? So, you know, this kind of question you have to like, okay, what am I going to do? You know, you are thinking about it, you keep on checking. But then if you know this topic, you can easily find the number right away. Okay? And of course, we have so many applications of this. Later on, we will have videos of applications of this topic, modular arithmetic and algorithms. It has several applications. Later, we are going to look at those applications in other videos. Okay? So this is a system of linear congruency. We call it system because it's more than one. Okay, more than one linear congruency. It's more than one. It is more than one linear congruency. So we call it system of linear congruencies. So how do we solve this kind of question? With the Chinese remainder theorem, it states that if you have a system of linear congruencies, like you have x is congruent to A1 mod M1, x is congruent to A2 mod M2, x is congruent to A3 mod M3. I want to explain the theorem, then we can solve this problem. Okay? Up to this fact, up to, if you have, when x is congruent to an mod mn. Okay? Where number one, because it has conditions. It has conditions. Okay? M1, M2, M1, M2, M3, up to Mn are relatively prime integers. They are relatively prime integers. Have to. As you can see, 5 and 7 are relatively prime integers. Okay, the modulo, they are the modulo M1, M2, M3, M4, up to Mn. They have to be relatively prime. Okay, this theorem applies to only, in fact, this theorem and the back substitution method, what we are going to discuss would just be for relatively prime integers. Okay? And number two, M1, M2, M3, up to Mn, okay, up to Mn, are positive integers greater than 1. Positive integers greater than 1. They are greater than 1. Okay? And then the A1, A2, A3, up to An are integers. Positive integers are positive integers. Okay? They are positive integers. Now, what the theorem is saying is that when you have this, with these conditions, okay, the conditions, with these conditions, what the theorem is saying is that you have, then you have M, I'm going to use uppercase M as the product of the moduli, okay? M1 times M2 times M3 times up to mn. Okay? Times up to mn, such that 0 is less than or equal to x is less than or equal to m. Okay? You have a solution, you have a unique solution. Okay? X is the unique solution. X is the unique solution. Unique solution. Between 0 and m. That is the Chinese remainder theorem. That is the Chinese remainder theorem. So when you have a system of linear congruences whereby the moduli are relatively prime, the moduli are positive integers, each modulo is a positive integer greater than 1. This A1, A2, A3, the numbers here are positive integers. Then you have a unique solution, okay, whereby 0 is less than or equal to the unique solution, and that unique solution is less than the product of the moduli. That is the Chinese remainder theorem. Now, let us now solve this problem. Let's solve it and let's check it. Okay? Let's solve it and let's check it on that. So look at, I'm going to do it step by step. We will solve two system of two congruencies, two linear congruencies, and we will do another example. We'll do another example. Let's do at least 2 examples in this video. We'll do this case of 2 linear congruencies, and then we will also do another example of 3 linear congruencies. Okay? So work with me. We will do it step by step so that you understand it very well. Okay? So when you have this, we will write out our A1 is 4, and I'm going to we are going to use the yellow chalk to circle what we are going to use. I'm going to use yellow chalk. A1 here is 4. Our A2 is 6. We shall use this. So I'm just going to circle it right now. M1 is 5. As you can see, 5 and 7 are relatively prime. So this satisfies these conditions. That is why we want to use this theorem to do this. So M1 is 5, M2 is 7. And we will go ahead and find uppercase M. Let us multiply the moduli. So this is M1 times M2. So M is 5 times 7. So M is 35. Okay? We have that. So remember, this is lowercase m. This is lowercase m, and this is uppercase m. Now, I'm going to have the uppercase m with subscript, uppercase M1. This is lowercase. Okay, this is lowercase M1. So after first of all, we wrote this A1, A2, M1, M2. Then we find the product of the moduli, uppercase M. Now let's find the moduli that applies to each congruence based on the product. So this M1 is M, big M over M1. So this uppercase M1 would be 35 divided by 5. So this uppercase M1 is 7. I will use it, so I circle it. I am circling everything I'm going to use to find my answer. Okay, somebody might ask me, hey, Mr. C, why don't you just use M1 to be 7? Okay, and you can do it. You can, like this big M1 to be small M2. You can do it, however, you need to be careful. If you have more than, when you have set of 3 linear congruencies, set of 4 linear congruencies, set of 5 linear congruencies, you have to be careful if you do that. So I will encourage you to do it like I'm doing it. However, you can say, somebody might say, hey, this is just 2 linear congruencies. Why don't you just use M1 as lowercase m2? That is fine for this case. Okay? But we shall do 3 linear congruencies and you see what I'm talking about. It's good you just do it like I'm doing it. Okay? Now, the uppercase M2 will be M over lowercase m2. So of course that is your 35 divided by 7. So our m2 will be 5. We shall use this, so we are going to circle it. Okay. So do you see step by step what we have done? Step by step what we have done. All right. We shall now find the inverse. Okay? We're going to find the inverse of what? Okay. So we'll say let y1 be equal to the inverse of m1 mod m1. Okay, uppercase m1 mod lowercase m1. Inverse of that. See that? Let y1 be inverse of uppercase uppercase m1 mod lowercase m1. So it goes back to our inverse. We have to find our inverse. Okay. So this means that y1 would be inverse of 7 mod 5. Inverse of 7 mod 5. That is our y1. Okay. Before we find the inverse, let us find the GCD. And we know the GCD is going to be 1 anyway. But let's find it, because from there we can get the inverse. We will get the Bezout coefficients and then get the inverse. So we have our GCD of 7 and 5. 7 is 5 times 1 plus 2. Okay? So 5, let's do it here. GCD 7 and 5. 7 is 5 times 1 plus 2, right? And 5 is 2 times 2 plus 1. Okay? 2, please, before this, it is my assumption that you have viewed the videos. If you go to this website, you look at videos, and you have to start from the beginning to follow this. So it is my assumption that you actually know this, because we have done this before. So we are just reviewing what we've done before. So if you do not understand what I am doing now, then you need to stop. You need to pause. You need to stop this video and go back and start from the top, first video in the playlist. You need to. If you don't understand what I am doing right now, you need to stop and start from the first video in that playlist. Okay? So 2 will be 1 times 2 plus 0. So this is our GCD here. This is our GCD here. GCD is 1 because the remainder is 0. But we will need to find from here, to find the inverse. We need to find the inverse. So we now have from here 1 is 5 minus 2 times 2. Okay? Which is equal to 5 minus, from here, 2 is 7 minus 5 times 1. So this 2 is 7 minus 5 times 1. Okay, 7 minus 5 times 1 and times 2, times this 2. Okay, so this is 5 minus 7 times 2. Minus times minus is plus. 5 times 1 times 2. So this is 5 times 1. 5 times 1 plus 5 times 1 times 2 minus 7 times 2. So this is 5 times 1 plus 5 times 2 minus 7 times 2. So this is 5, 1 plus 2. 5, 1 plus 2 minus 7 times 2. So this is 5 times 3. 5 times 3 minus 7 times 2. Okay? And let's check it. 15 minus 14 is 1. 15 minus 14 is 1. So but we are looking for inverse of 7 mod 5. So this will be 1 is equal to 5 times 3 plus 7 times minus 2. Okay? Because we want only 5 and 7. Alright, so the inverse of 7 mod 5 is equal to negative 2 mod 5, and that gives us 3. That gives us 3. So y1 is 3. y1 is 3. We'll circle it. You circle it. Now y2, let y2 be inverse of m2 uppercase m, uppercase m2 mod lowercase m2. So y2 is inverse of 5 mod 7. Inverse of 5 mod 7. That is our y2. Okay? And we can see it right here already. Inverse of 5 mod 7 is 3. Inverse of 5 mod 7 is 3. Okay? Is this 3 also? So our y2 is 3. Alright. We are almost done now. So our x, so this is the Chinese remainder theorem. Our x is equal to a1 m1 uppercase m1 y1 amy. Amy. Is it Amy or Amy? Amy. Amy. Hey. Amy. A1 M1 Y1 plus A2 M2 Y2 mod M. Mod M. This is our formula here for x. Okay? That is our formula. You see, that is why I said let's circle what we shall use. Yeah. Mod big M. So let's circle big M also. Big M is 35. Yeah. There you go. So we're using the big M, the product of the moduli. Yeah. So like I said, from the Chinese remainder theorem, 0 should be less than x. 0 should be less than x, less than or equal to x, okay, because in some cases x can be 0. 0 is less than or equal to x, and x is less than the product of the moduli. Okay? So, and if you have three cases, if you have three congruencies, we will add plus a3, m3, y3. That is the formula. Alright, so let's do it. X will be a1 is 4 times 7 times 3 plus, I'm going to use bracket here, okay, plus a2 is 6 times 5 times 3. Close this, then mod 35. Mod 35. So x will be equal to 4 times 7 is 28. 28 times 3. 3 times 8, 4. 2. 3 times 2, 6 plus 2, 84. 84, let's use parentheses. 84 plus 30 times 3, 90. Mod 35. Okay, 84, so this is x will be equal to 84 plus 90 is 174 mod 35. Let's use a calculator to be fast. Okay? Let's use calculator to be fast. So 174 divided by 35, this is 4 point something. 35 times 4, 140. 174 minus 140, okay? And that is 34. X is 34. Our answer is 34. And this becomes our answer. 34. Okay, let us check it. Let us check it. 34 divided by 5 will give us 6 remainder 4. Because 6 times 5 is 30 and remainder 4. Okay, so it works here. And then 34 divided by 7. 7 times 5 is 35. So 7 times 4, 28. So 34 minus 28 is 6. Okay, so that works. 34 divided by 7 is 4, remainder 6. Okay, 34 divided by 5 is 6, remainder 4. And 34 divided by 7 is 4, remainder 6. So that's the answer, 34. Then, let me state this, okay? Another addition to the, I just remembered it now, to the Chinese remainder theorem. So, all, once you find a solution, once you find a unique solution, you can also have multiple solutions congruent to that modulo. So what is this saying? Okay, so remember x is just the smallest number that would work. But in addition to the Chinese remainder theorem, you can add it, okay? Or just go to this website and you see it. Or you can just, if you're taking notes, go ahead and add it as well. So we have a solution. X is 34. And this is in mod 35. We also have other solutions. Okay? Other solutions. We can have x is 69. 69 would work. 69 divided by 5. 13 times 5 is 65. So it's 13, remainder 4. Okay? And then 69 divided by 7 is 9. 9 times 7 is 63. 9 remainder 6. So 69 would work. Okay, because you just list everything in the congruence class. Just keep adding this. X is 69. X could also be 69 plus 35. Just you keep on adding that. 104. 104 plus 35. You keep on adding that, okay? And I can do this offhand. It's just that you might say, hey, Mr. C, why don't you just do this addition offhand? I can do it offhand. It's just that, I want us to save time. Okay. 104. 104 divided by 5 is 20. 100. Remember 4. Okay. So 104 works for the first one. Then 104 divided by 7. 7 times 13 is 91. 7 times 14 is 98. So 14. Okay, 14 is the quotient. Remember 104 minus 98. Remember 6. It works. Okay, you just keep adding 35. Just equivalent classes of that modulo. Okay? Congruence classes of that modulo. Does that make sense, folks? Does it make sense? You see all the steps. You see all the steps, you keep doing that. Okay? Alright. The calculator will give you only, the calculator I have here will just give you the first answer, 34. It should give you that. It should. Okay? Because you know that 69 mod 35 is still 34. 104 mod 35 is 34. 139 mod 35 is 34. Okay? Alright, let's do another example and then we can call it a day. Okay? Let's do another example. Let's do a set of 3 linear congruences. Set of 3 linear congruences. Example 2. 3 linear congruences. So x is congruent to 2 in mod 7. X is congruent to 3 in mod 9. X is congruent to 5 in mod 10. So this is equivalent to saying this is similar as saying, what is the number that when you divide it by 7, the remainder is 2? When you divide the same number by 9, the remainder is 3. And when you divide the same number by 10, when you divide the same numero by 10, okay, the remainder is 5. The remainder is 5. What is that number? Okay, what's the smallest positive number? Smallest positive number that when you divide the number by 7, the remainder is 2. When you divide the number by 9, the remainder is 3. And when you divide the number by 10, the remainder is 5. Okay, first of all, the moduli 7, 9, and 10 are relatively prime. If you are using this calculator, the calculator on this website, if you put something that is not relatively prime, like if you put 7, 8, 10, it will not solve it. It will tell you, it will give you an alert. Hey, no, it won't solve it. It will quit. And it will give you the alert only for relatively prime moduli. This theorem. Okay? The Chinese remember theorem. Only for relatively prime moduli. Okay, let's do this. We write A1. Our A1 is 2. Our A2 is 3. Our A3 is 5. So let's circle it. Then our M1 is 7. Our M2 is 9. Our M3, lowercase m, is 10. Our M, the product of the moduli, is 7 times 9 times 10. 7 times 9, 63 times 10, 630. 630. Okay, so I'm just going to write it again here. M is 630. So let's circle it. We shall use it. All right. Our M1, uppercase M1. Our uppercase M1 is M over M1. So uppercase M1 is 630 divided by 7. So uppercase M1 is 90. We need it. So let's circle it. So this is what I'm saying. You can also say 9 times 10, 90. If you want to, you can say 9 times 10. But, just like the previous example we just did, you could choose the other one right away. Yeah, you could say 9 times 10 if you want to do it that way. Okay, that M1 is lowercase m2 times lowercase m3. If you want to do that. Okay, but I prefer this. I prefer doing it this way. Okay, then M2 is M uppercase M over M lowercase m2. So M2 is 630 over 9. So M2 is 70. We shall use it. So let's circle it. Okay. Okay, M3 is M over M3. So M3 is 630 over 10. And our M3 is 63. We circle it. Alright, folks. We finna do some work now. We're fixing to we're fixing to do the work now. We're fixing to, or we finna do the work. We finna do the work now. We finna do the work now. Or not I'm finna. I'm fixing to. I'm finna. Or I'ma do the work. Okay, now let's get this done, folks. The next thing is to find the inverse. The inverse. Next thing is to find the inverse. Let y1 to be inverse of m1 mod m1. So let's write it here. y1 inverse of m1 mod m1. M uppercase 1. M subscript 1 mod lowercase m subscript 1. So inverse of, so y1 is inverse of 90 mod 7. 90 mod 7. Let's find our m1. Inverse of 90 mod 7. Okay? Inverse of 90 mod 7. Ooh, I got that. I got it. Ooh, I got it. Okay. 90 as 7. GCD of 90 as 7. 90 is 7 times 7 times 10 is 70. 7 times 12 is 84. 7 times 13 is 91. Okay, so 7 times 12, 84 plus 6. Right? 7 times 12 plus 6. Then 7 comes here. 7 is equal to 6. 6 times 1 plus 1. 6 is equal to 1 times 6 plus 0. So the GCD is 1. Okay? But let's get the inverse now. Let's get the inverse. Let us get the inverse from here. 1 is equal to 7 minus 6 times 1. That is from here. And this is equal to 7 minus this 6. This 6 is 90 minus 7 times 12. Then times this one. Times this one. So this is 7 times 1. Let me just put 7 because 7 times 1, which is 7. Minus 90 times 1, this 1. Minus times minus plus. Plus 7 times 12 times this one. Times 1. So this will give us 7 times 1. 7 times 1. Plus 7 times, 12 times 1 is 12. 7 times 12 minus 90 times 1. Okay, so this is 7 times 1 plus 12 minus 90 times 1, which is 7 times 13 minus 90 times 1. And that works, okay? From here, 7 times 13 is 91. 91 minus 90 is 1. Alright, so we are looking for inverse of 90 mod 7. Okay, so this is 7 times 13 plus 90 times negative 1. Okay, 1 is equal to this. So the inverse of 90 mod 7 is negative 1 mod 7. Okay, it's negative 1. So negative 1 mod 7 is 6. It's negative 1 mod 7. Inverse of 90 mod 7 is negative 1 mod 7, and that is 6. So we got our y1 to be 6. We write 6 and we circle it. We will need it. Okay? Now we do y2. y2 is inverse of m2 mod m2. So y2 is inverse of 70 mod 9. 70 mod 9. Okay, inverse of 70 mod 9 is m2. Inverse of 70 mod 9. And y2 would be equal to, so inverse of 70 mod 9, which is 97, which is good, we did it here. Inverse of 70 mod 9. Oh, sorry, this is 90 and 7. We are looking at 70 mod 9. So we have to do 70 and 9. Oh, come on. You know, it wasn't like the example 1 that we just got right away. This one, without, yeah, because this is 3 cases, yeah. Okay, let's do it. GCD of 70 and 9. GCD of 70 and 9. So, GCD of 70 and 9. And 9. Then we can get the inverse. So 70 is 9 times 7, 63. Okay, plus 63 plus 7. Okay, right? 9 times 7, 63 plus 7. That's 70. Okay. 9 is 7 times 1 plus 2. 7 is 2 times 3 plus 1. Okay, 2 times 3, 6 plus 1, 7. 2 is 1 times 2 plus 0. So GCD is 1. Okay? But we now have to start from here to get, our inverse. We're looking for 70 and 9. Okay, so 1 is equal to 7 minus 2 times 3. And that is equal to 7 minus, this 2 is 9 minus 7 times 1, then times this 3, times this 3. Okay? So this will be 7 minus 9 times 3. Then we can say 7 times 1. Okay? 7 times 1 minus 9 times 3, then minus times minus is plus, plus 7 times 1 times 3. So this will be 7 times 1 plus 7, 1 times 3 is 3, 7 times 3 minus 9 times 3. So this means that 1 is equal to 7 times 1 plus 3 minus 9 times 3. So which is 7 times 4 minus 9 times 3. And that is correct. 7 times 4 is 28. 9 times 3 is 27. So 28 minus 27 is 1. Okay? But we are not done, because we need 70 and 9. We need 70 and 9. So this will be equal to, now we have to use this 7 now. This 7 is 70 minus 9 times 7, then times 4 minus 9 times 3. This 7 here. Then this 4 is this 4. Okay? We covered this already, modular inverse. Okay? So this will be 70 times 4 minus 9 times 7 times 4 minus 9 times 3. So this is 70 times 4 minus 9 times 28 minus 9 times 3. So this is 70 times 4 minus 9, 28 plus 3. Okay? Minus 9, 28 plus 3. Which is 70 times 4 minus 9 times 31. Okay? And this is 70 mod 9. Okay? Not 9 mod 70. Okay? If it's 9 mod 70, then we fix this. But 70 mod 9, we just, is 4. So we don't need to waste our time on this. 70 times 4 plus 9 times negative 31. But the inverse of 70 mod 9 is 4. Is this 4? Let's check it. Let us check it. 70 times 4 is 280. 9 times 31 is 279. Yeah, 279. So 280 minus 279 is 1. It's good to always check it. So this y2 is 4. Let me write this 6 1. Y2 is 4. Okay? We circle it. Now, y3 will be inverse of m3 mod m3. So y3 is inverse of 63 mod 10. So y3 will be what? So inverse of 63 mod 10. Alright. So let's do it. Let's do it. Let us do it. GCD of 63 and 10, of course, will give us 1. 63 is 10 times 6 plus 3, right? 10 is 3 times 3 plus 1. 3 is 1 times 3 plus 0. So this 1 is the divisor, okay? So GCD is 1, but we will get our inverse, the Bezout's coefficients, okay? We'll get the inverse from here. So 1 is equal to 10 minus 3 times 3. Okay? Let me know. 10 minus 3 times 3. So this is equal to 10 minus this 3 is, we now put parentheses, 63 minus 10 times 6, then times this 3. Times this 3. Okay? So this will be 10 minus 63 times 3. Minus times minus is plus. Plus 10 times 6 times 3. So this will be 10 times 1 plus 10 times 18. 6 times 3 is 18. Minus 63 times 3. So this will be 10, 1 plus 18, 10 times, parentheses 1 plus 18, minus 63 times 3. Right? So this means that 1 is equal to 10 times 19 minus 63 times 3, which is 10 times 19 plus 63 times negative 3. Okay, we need inverse of 63 mod 10. Now let's check this first. Let us check it. 10 times 19 is 190. 63 times 3 is 189. So it works. 190 minus 189 is 1. Okay, now we need inverse of 63 mod 10. So inverse of 63 mod 10 is equal to this negative 3. Negative 3 mod 10. We want to use all this positive stuff, okay? Not negative. Negative 3 mod 10, which is 7. 7. So y3 is 7. Alright, folks, we are almost done. I hope we get it right, honestly. We have spent time on this. We have spent time on this, right? Okay, I hope by the grace of God, by the grace of the Almighty God, by the grace of Jesus Christ, I hope we get this correct. I hope we get it right. Okay, so our x is equal to A1ME, A1M1, Y1 plus, let's use parentheses here, okay? A2N2 Y2 plus A3 N3 Y3 mod M, the product of the moduli. So our x is, I use bracket here, so this is 2 times 90 times 6 plus 3 times 70 times 4 plus 5 times 63 times 7. Okay? Mod 630. 630. So our x will be, let's, 2 times 6 is 12. 12 times 9 is 108. 1080 plus 3 times 4 is 12 times 7, 84. 84 times 10, 840. 840 plus, let's use calculator. So to be faster, and 35 times 63. 2205. 2205 mod 630. So our x is 2205 plus 840 plus 1080. 4125. 4125 mod 630. So our x is 4125 divided by 630, 6 point something, 630 times 6, and then subtract from 4125. Our x is 345. And this becomes our answer. That's our answer, 345. Okay? Can we check it? Let's check it. Okay? 345 divided by 7. 345 divided by 7 is 49 point something. So 49 times 7, subtract from 345, it gives you 2. So this works. Okay, it works for the first one. Works. 345 divided by 9, 38.333. 38 times 9, subtract from 345, gives you 3. Works. 345 divided by 10, of course, gives you 340. And that's 5. Okay, 340. Remember 5. Yeah, it works. Thank God. Okay, this worked for the 3 of them. I hope you understood it. Thank you so much for listening to this video session. If you don't like this method, if you do not like this method, then watch out for the next video where we shall do the back substitution method. Some people prefer back substitution method. I mean, that's fine. I prefer the back substitution method. We shall do the same questions we did here. We shall do those same questions with the back substitution method. Okay? Thank you so much for listening to this video session. If you have any questions, please feel free to ask. And you have a great day.